2. Yeah.
Hello and welcome to this webinar hosted by Metering and Smart Energy International and sponsored by OMNETRIC Group. I'm Claire Falkvane, Managing Editor of Metering and Smart Energy International. Our sponsor today, as I've mentioned, is OMNETRIC Group. A joint venture between Accenture and Siemens, OMNETRIC went live in April 2014. The joint venture broadens the scope of collaboration between the companies to include distribution management, grid control, demand response, and smart grid analytics. Combining the power and knowledge of Siemens and Accenture, OMNETRIC Group is committed to working with utilities to improve the efficiency and reliability of the grid. Active demand response is the ability to manage consumer demand resources in a way that supports balancing of renewable energy resources, extends the value of demand response from transmission to distribution, ultimately dealing with any type of grid stress in a near real-time fashion. Some utilities are already embarking on the second phase of demand response. They're no longer looking at demand management as a passive sideline component of their business. Changes in consumption, the integration of renewables, and more sophisticated control technologies are introducing the opportunities for utilities to more actively manage demand. Now, joining me today is Sachin Gupta of OMNETRIC, along with Rémi Guérard-Verdier of ERDF in France, and Brett Feltman, a Senior Research Analyst from NAVIGANT Research. Sachin, I'll hand over to you.
Thank you, everybody, for taking the time to join the webinar today. The intent and the component that I'm going to talk about is how technology can help enable active load management. From an overview perspective, one thing I did want to talk about is who OMNETRIC Group really is. OMNETRIC was formed as a joint venture between Siemens and Accenture, helping to bring to market new solutions that help bridge the gap between informational technologies and operational technologies on the behalf of utilities, helping create a more comprehensive solution. OMNETRIC gets to draw inspiration from its parent companies. From Siemens, we are able to bring engineering and energy technology expertise. From Accenture, we're able to bring system integration and service expertise, as well as the Accenture proven delivery methodology for implementing technology. Together, we're able to bring together and create a unified organization and a holistic approach to helping utilities bridge the gap with smart grid-related technology infrastructure deployments. As we know, energy demand is rising worldwide. There's a lot of different factors that play into this. Population increase. I think one of the other components here is that anything that we create as a society generally tends to consume electricity. And that actually places a lot of stress on the grid, both from a geographic perspective, but also an infrastructure perspective. In certain parts of the world, the infrastructure is aging. Other parts of the world, there's new infrastructure, there's new challenges, there's need for being able to transmit a greater amount of electricity. Also, with the penetration of renewable energy resources, we're starting to see that the energy supply is becoming much more decentralized. That in itself presents many different challenges for utilities and operators that are out in the marketplace. Generally from the most basic concept, we've always looked at demand response as being able to balance supply and demand. But with the penetration of renewable energy resources, we now have an intermittent supply of energy that we also need to take into account. And on the other end of the broad spectrum, outside of basic demand response, we look at more active load management. How can we balance load within the distribution network? How can we take in inputs from distributed energy resources, traditional forms of generation, and consumer demand-side resources, and really package up a comprehensive solution that allows a utility to, one, manage flexibility within the marketplace, two, provide balance for localized grid stress, but then also have an opportunity, depending on market structures geographically, to take advantage and potentially create new revenue-generating opportunities. Demand response has always existed. When we looked at what we would say the grid, pre-smart grid technology and infrastructure, When we looked at centralized unidirectional communication, even in this context in the United States, demand response has existed for 30 years. It's been challenging. Generally, it's been hard to understand how consumer demand resources have impacted the grid because there was really no way to provide measurement and verification. There's really no way to understand that when you push the button and you execute a load curtailment command to a consumer, how much load is actually being shed because there was no granularity of data or any real-time data that existed. Yet demand response continued to persist with certain utilities as kind of a key asset for emergency load shedding or peak shaving. When we look at today's grid, at least the investments being made in infrastructure, a lot of that investment is being made into the distribution network, and we have access to much more data than we've had previously. And from a technology platform standpoint to manage active load management or to provide active load management, it's how can we bring together all these different bits and pieces of information collectively as a whole and make load management more intelligent or more active. We have penetration of renewables. We have meter data coming in. We have SCADA data coming in. We have different consumer demand-side resources that can be connected from residential customers to C&I customers all the way up to even electric vehicle charging infrastructure. And how can we provide and leverage technology to optimize load balancing with these characteristics? We have to first look at how to transition from basic demand response to more of an active load management component where we are taking into account all the different variables. If you looked at technology in the past, generally technology in the past was created to support a single objective, which was emergency dispatch or emergency peak shaving. And those forms of technology really helped provide what we would say a shotgun-like approach, where when a load curtailment command was issued by the technology to the consumers, it dispatched it utility-wide, geographically, and in most cases, when you're trying to deal with localized grid stress, that approach doesn't work because it costs time, money, and it overburdens the consumer. The focus on technology here is to get consumers to participate, but also make it as easy for them to participate as possible. And new forms of technology have come into the marketplace that really allow us to start surgically targeting loads. If there is a particular substation that is in grid-related stress, we can execute curtailment commands to that particular substation and the consumer loads behind that substation. If there is a balancing problem behind a particular substation between renewable energy resources and consumer demand resources, the first thing that we can do is find a way to provide balance by executing load curtailment commands or employing storage or other needed measures behind that substation. When we look at the concept of active load management, it's really to take and tie together what we talked about with traditional load management, but also bringing and bridging the gap between active load management. It's at the end of the day being able to bring together kind of into a single application all the different facets that we talk about, both traditional forms of generation, renewable forms of generation, and the consumer. And the intent is that technology will help provide automation, technology will help provide optimization, and technology will ultimately help provide, in certain circumstances, the cheapest form of dispatch capable for an operator. As we go through and we look at how an actual system is set up, depending on the operator, depending on the utility, key data inputs would be the SCADA systems, the billing systems, the energy management systems. If we have access to smart metering information, being able to take in that interval data, connectivity to a wholesale marketplace, which would allow us to transact load into that marketplace or at least get real-time pricing. Being able to manage generation, both traditional forms of generation and then generation, as we would say, that's transmission scale, but generation that's also distribution level scale that consumers have deployed like PV. And then actually mapping in consumer loads, which is the traditional demand side resources, and creating harmony and creating balance and letting the application take in the inputs, having the application configured in a manner that with automation we can create an application that provides end-to-end active load management. With anything, technology is technology, but technology becomes smarter with integration, and integration really becomes the driver here. As utilities go out and operators go out and continue to invest in what we call smart grid related technologies, they have access to a lot more information. And that information can be very helpful if it's used in the right sort of way, and integration becomes key to that. At the end of the day, you can see from this slide and as it rendered, short-term thinking leads to long-term complexity. Short-term thinking, you're not necessarily dissecting the messages the right way. There's repetition of integration. Whereas with long-term thinking and planning, we can clearly go out and be able to draw in all of the necessary inputs and outputs in a efficient and, more importantly, scalable and flexible manner. So as loads grow, as utility demands grow, the application and the technology itself is able to sustain that in the most efficient, economic way. When we look at how technology will come together, at the end of the day, everything should work in real time. And a lot of this is kind of the utopian view. A lot of this is based on the different infrastructures that different operators have. It's based on the different types of integration components that are available to us. But kind of the technology for active load management should support real-time optimization, dispatch, and control. We're getting data in. We're able to forecast and control both traditional and non-traditional forms of generation. We potentially have different storage solutions involved, and we have consumer demand-side resources that are also taking part. And depending on system configurations, depending on pricing, depending on how the market structure is set up, the actual application is able to go through in near real time every 5 minutes, every 15 minutes, and forecast supply and demand locally at a particular distribution substation or at a system-wide level, and be able to create harmony and balance on an ongoing basis. So we don't run into problems where we have a supply shortage. We don't run into problems where we need to resort to rolling blackouts, etc. So that's the intent of technology from that perspective. I will now transition over to Remy, who will provide an actual case study and lessons learned from projects in Europe.
Thank you. I will start with briefly presenting the GRID4EU project, which is a European project, and then I will directly move to what we are doing in GRID4EU regarding demand response. So GRID4EU is a large-scale European project, and in this project, with the help and the funding of the European Commission, we are gathering 6 electricity distribution system operators, 6 DSOs, covering altogether more than 50% of the metro electricity customers in Europe. So in this project, and ERDF, and I'm working for ERDF, is the coordinator, NL is the technical director, Iberdrola in Spain is chairman of General Assembly, Chess Distribution in Czech Republic, RV in Germany, and Vattenfall in Sweden are also participating. In this project, we are testing with all our 27 partners different use cases over 51 months, and the project will end next January. It means that at this period of the project, we already have real results coming from the field. This is the list of, on the map you can see the 6 demos. So GRID4EU consists of 6 demos in 6 countries. And you can see all the 27 partners. It means that we are working with utilities, of course, research center, universities, but also manufacturers like Siemens, ABB, and Alstom. In the project, we are testing several use cases, and today we will focus on the French demo in Nice, on the French Riviera. And as you can see, there is 4 use cases, one on islanding, for the reduction of the power demand, one regarding how to manage the PV production on the low voltage network, and the last one is to encourage residents to adopt smarter habits and to change their behaviors regarding the grid constraints. So this is the most exciting part of the presentation, is to directly deep into the demo. The site of the French demo is Carros. Carros is a small town in the French Riviera, very close to Nice, and within the Eco Valley, which is a French national interest project. The Nice Grid project is being conducted in the center of the town and in its industrial zone. In this project, on one hand, we have to deal with the integration of massive decentralized photovoltaic generation connected on the low voltage grid. This is something quite specific in France, where 95% of the renewables are connected to the low voltage grid. In this area, 2.5 megawatts of PV are installed and thus connected to the low voltage grid, including more than 100 residential installations. This high penetration of renewable energy brings grid stability challenges, especially in summertime. As the graph highlights, undesired voltage levels tend to be reached in location along the low voltage grid. As a matter of fact, the distribution grid was designed to support winter load, is known enduring voltage outrange during the sun zenith, due to photovoltaic power production that cannot be absorbed by any load. On the other hand, while peak PV production might give rise to network constraints in summer, the area is subject to an average lack of local production on a yearly scale. Indeed, compared to the global French power system, this regional area is known as an electric peninsula, we call it like that, connected to the bulk power grid through a single transmission corridor, just a single 400 kV line. The local generation represents only just 10% of the consumption load in winter. The area can hence be vulnerable under load peaking condition to the risk of single contingency conditions. On summer, because of the Mediterranean weather condition, the risk of some forest fires is important, so that events of disconnection on the aerial high voltage line may occur as well. So this is quite a tricky part of France for ERDF there. As mentioned previously, we are testing on the field 4 use cases, and I will briefly detail them. To solve these constraints, the demo has defined the following use cases. The summer use case, the management of maximized PV production on the low voltage network with respect to constraint and flexibility program. So in this one, a massive penetration of the renewable in the low voltage network may result in localized network constraints. And the targeted solution in this use case is to activate consumption and storage in predefined way near the constraint point, in order to prevent overvoltage and to minimize PV inverters disconnection. This is what we are testing. We are testing that in the orange area. In the winter use case, the reduction of power demand in a network area. This type of operation can be used both by the DSO, ERDF, or the TSO. In France, the TSO is RTE. Request to prevent electrical constraints on the network to help supply-demand balance and to prevent customers from power outages. Different levers can be used to achieve this goal, such as flexibilities related to customer appliance and batteries located at customers' premises, as well as network batteries. The aim here is to achieve 3.5 megawatt load reduction during the winter, and the area for that is exactly the same. This is on the orange areas on the map. We also have an islanding use case. In this one, we would like to island the network and then to disconnect this area from the national grid or the connected grid, and we would like to perfectly balance the local production and the local consumption without any additional generation, like any turning machine, like a diesel system. So this is the very small red area in the right of the map, and the name of this area is the Dockstrachel. So this is where we are doing some islanding operation. And the last use case is encouraging customers to adopt smarter habits in accordance with instruction. So during critical periods for the electric grid, the aim is to nudge customers into changing their electricity consumption behaviors by stopping, moderating, or postponing some of their electrical devices use. When instructions are sent, due to network constraints, the consumer is informed about the ongoing incentive period. General suggestions and information will be sent to help them act before, during, and after these periods. Their consumption, PV production information, combined with weather data and storage data, will be available to improve the impact of the actions and ensure that efforts benefit them. The key goal here will be to promote the active participation, encouraging them to control their energy consumption and thus help to reduce greenhouse gas emission as well as the amount of the bill. As you can see, active demand is tested in the summer as well in the winter. So let's begin with the summer use case. In summertime, to encourage customers who live in an area where PV production could be a problem, EDF, which is the supplier, the retailer, has put in place two offers. The first offer relies on remotely controlled water heater. The water tank is charged. We switch them on from 2 p.m. onward, when the PV installations are the most productive. Water heaters are switched on through a dry contact with the smart meter. The water tank is used as a storage asset, and it can absorb the excess PV generation within the distribution grid. These clients can act also on a voluntary basis using the solar bonus, as they are advised with a text message and or an email the day before. The client who subscribe the solar bonus, we call that SBO, the solar bonus offer, have 4 off-peak hours between noon and 4 p.m. on 40 sunny days each summer. So during 40 sunny days in the summer, they have more off-peak tariff than the other people. Electricity consumed during off-peak hour is 1/3 cheaper as the one consumed in on-peak hours. While these off-peak hours used to happen during the night, we decided to put them in the afternoon as well to encourage customers to absorb photovoltaic overcapacity, and we use the text message and the email. What is the beauty here of GRID4EU is that we are doing active demand, not only, and we will see that during the winter use case, but not only to reduce the consumption, but to bring more load on the grid during the summer. So this is quite an habitual way to use active demand. The results of the solar bonus offer is an increase of 12% of the instant power consumed is reached by the solar bonus participants. The impact for the grid stability of these efforts of residential participants is correlated to the share of participants, of course, in the area where the use case is tested. At the end, an average decrease of 2% of the power consumption between noon and 4 p.m. is reached every solar day. This is the 40 days where we apply the solar bonus to the consumers. Combined with the action of the remotely controlled water heater, the decrease of the instant power consumption is of 7% in the 7 solar districts where we are testing this solar bonus day and the controlled water heater. So let's see now the result of the winter use case. In winter, participating customers were encouraged to change their behavior and limit their consumption through non-financial incentives. And of course, the reduction of the monthly electricity bill linked to the reduction of energy use. So we did here a lot of explanation about to convince the people to change the behavior without any financial incentive. In addition, they also had the possibility to have their electric heating remotely controlled by the aggregator. So there is an aggregator, and this aggregator is able to switch your electric heating system off and then to switch it on again. And we have measured for each house what is the maximum time with the electric heating system off, if you don't, in order to avoid to make the customer freezing in the house. We know that it's about 10 minutes to 12 minutes, and then after 12 minutes off, the heating system is on again. And we doing that, we try to avoid the famous rebound effect, which is very difficult to handle for the utility. The results are encouraging, as these participating households lowered their power consumption by an average of 20% on peak days between 6 p.m. and 8 p.m. Participating businesses corresponding to about 10 megawatts of the subscribed power in the area reduced their power consumption in the peak evening period by about 10%. Nevertheless, it's important to mention that this achieved load reduction is lower than the value forecast by aggregators. So, at the very beginning of the project, based on the calculation coming from the aggregators, we believed that we will be able to achieve a bit more, but after 2 winters of tests, we know that it's not so easy to achieve load shedding, a large amount of load shedding, if we are without any financial incentive. Although experimentation results show a high variability of the load shedding, level of load shedding vary depending on the day of the experimentation. The average load reduction, which one day can be up 4 times lower than the one reached 20 days after, for example. These variations are very difficult to predict. Currently, it's difficult to predict the actual load shedding that could be enabled by client behavior change. So this is one of the conclusions of the tests on the field. Very difficult to anticipate, and thus to take this for granted as a network manager. The flexibilities are not very always easy to anticipate, and then to manage the grid accordingly. Before the conclusion, we would like to show which technologies enable these use cases. Are quite simple. Before all, the tool enabling active demand is the Linky smart meter. Linky smart meter is the smart meter developed for ERDF, by ERDF and for ERDF. This next generation electricity meter is a key element in the demonstrator project. It remotely measures household power consumption and generation at regular intervals to optimize the management of the electricity distribution grid. This new type of meters also lets participating customers take part in the winter and summer use case through a relay installed inside the meter. As of today, more than 2,500 meters have been installed in the demo area. To enable the winter use case, the radio relays are necessary to control electric heating. Consequences are higher installation and maintenance cost and lower customer involvement. We do believe that we as a utility have to make things simple for the customers. And as you can see on the pictures, on the right, the green Linky smart meter and the famous radio relay, so making communication possible between the smart meters and the smart plug, and the small relay to manage the electric heating system. So what are the main lessons learned from this demo? So numerous participants for a higher effect. Of course, if more people are involved in the demo, it's better, and we will have more. It's more efficient. The efficient customer involvement requires several things. First, the use of interesting incentives, and we know now that without financial incentive, it's quite a challenge to ask people to change their behavior, even if they believe that it's good for them, it's good for the bill, and it's good for the planet. It's not always easy. And beyond the meter infrastructure, we believe that it should belong to the customers. If they belong to them, they have a better involvement, and it's also reducing the cost for the aggregator. The electric hot water tank can be used full storage for PV generation, and for that in France we have it's quite a chance for us, because we have 12 million water heaters, and we can manage them, switch them on or off remotely. And so ERDF is doing that. The water heater remote control was done in the middle of the 90s to provide load during the night for the French nuclear power station. And now it's quite a chance for us, because we are using the water heater and the remote control on them to do active demand, and in the NIS grid project to bring more load on the grid during the afternoon to absorb the PV generation, and the infrastructure for that is already in place. And the load shedding must not be overestimated by clients or by the aggregators. This is one of the key takeaways from NIS Grid and GRID4EU. Most of the aggregators are quite optimistic on what could be achieved by the customers. The results from the field show that it's a bit less than the amount that was expected. Thank you, and now I hand over to Brett Feldman from NAVIGANT. He will present you global trends concerning demand response. Thank you.
Great, thank you very much. We're going to have some interesting information from a real-world project. and I'm going to take a little step back and give a higher level view of trends in the demand response industry, and then I'll give some examples as well. I think Sachin and Remy already touched on a lot of my points, so I'll be happy to try to get through these so we can get to some good Q&A. So I am Brett Feldman from NAVIGANT Research, part of NAVIGANT Consulting Group. And quick table of contents, I'll talk about some drivers for demand response as well as some barriers. We'll look at some of the leading state developments in the United States, and then we'll talk about a few international developments as well, and I'll end with some recent market forecasts that we've made in the demand response industry. So the list of the drivers, and we've already heard about a lot of these, so there are a couple from the technology side. First one is advanced metering infrastructure, just the ability to have more granular data, more timely data to be able to measure demand response in a quicker and more accurate fashion. So it's a huge difference from having monthly meters where you have to wait weeks or months even to get results, and you can't really see anything in real time. So it's a huge advantage. And then more on the customer side, I think Remy talked about some customer devices, but more generally things like smart thermostats, two-way communicating thermostats, and you see a lot of new devices coming out with more learning capabilities. So again, just giving the customer more control and having more of the two-way communication is key to being able to move demand response forward. And then on the policy or the market side, a number of opportunities. So typically, demand response has been focused on peak reductions, but now it's getting more of an ability to participate in ancillary services markets, things like 10-minute spinning reserve, or even down to 4-second frequency regulation type of a program. So those opportunities have more value associated with them. Renewable integration. So people might have seen on the right-hand side the duct curve, the duct chart from the California ISO due to increasing solar penetration. And I think Remy, on one of his slides, showed the winter load shape in France, which is kind of the French duct curve. Maybe that's the foie gras curve. But so in California, you have a similar dynamic with solar reducing the net load in the middle of the day, and then a quick ramp up as the sun goes down. So they'll need all types of flexible resources to respond. Dynamic pricing, so that was one of the components in the project that Remy talked about as well, getting away from flat prices and giving people more visibility into the real cost of energy so they know what it costs when they consume different end uses, so they can shift things around or reduce usage in response. And some other terms you hear like grid modernization, so that's just a more general utility transformation type of efforts, and we'll see a couple of the leading states that are going through that, just getting away from traditional vertically integrated utilities and centralized generation into more distributed types of systems and platforms. And then grid resiliency, which is maybe with more of the genesis of grid modernization. We've had some big storms around the world recently with large blackouts, and so that's led policymakers to look to ways to harden the grid, and that can be both on the wires and the steel side as well as the customer side, things like microgrids and demand response and distributed generation. So that's certainly a driver as well. And then the last one, environmental benefits. So in both the U.S. and in Europe, there are a lot of pressures to reduce carbon emissions. The U.S. Environmental Protection Agency recently came out with its Clean Power Plan on carbon reductions. And so NAVIGANT did a study to look at the ability for demand response to reduce carbon emissions, which a lot of people don't think about, but it is an opportunity, and it's the same as seen in Europe. Let's take a couple more on the drivers, and this goes maybe more to what Sasha was talking about with the systems and control. So you do need some kind of standards as opposed to every vendor having their own proprietary system, so you need a lot of interoperability, and there's a few examples here. There's Open ADR, Open Automated Demand Response, which is becoming more of an international standard. You can see on the right side the members, and it's growing in Japan and other parts of Asia and Europe. And there's also the U.S. Green Building Council's LEED program, Leadership in Energy and Environmental Design, which gives buildings points for energy and environmental considerations and demand response. In the past couple of years has been applicable for LEED points, so that's a driver for a lot of building designers and architects. And on a state level also, you see California putting in its Title 24 building code, some requirements for new large buildings and also retrofits of large buildings to require automated demand response capabilities. Talk about a couple of the barriers, and I think these have already been touched upon as well. So winter DR, we saw the need for that in France, but in the U.S., DR had typically been a summer resource until the last couple of years, and so in 2014 there was this thing called the polar vortex, where a huge part of the northeast and the mid-Atlantic of the country got an extreme cold snap in January of 2014, and it's not necessarily that the peak demand went up that much. It was more about natural gas constraints, because there's so much natural gas generation in the U.S. now due to gas prices. There's not necessarily the pipeline capacity to get that gas when it's needed. So some of the plants weren't able to get fuel, which led to outages, and that's something that a lot of regions are concerned about. So places like ISO in New England and the PJM wholesale markets are putting more requirements on resources for annual availability, which could be a constraint for some DR to participate in those types of market opportunities. And the other one, before we talked about solar on a macro level as an opportunity for demand response, but just to think about it on a more micro level, on an individual facility, if you're not in that duck curve situation like California, if a house puts on PV or a commercial building puts on solar, then that'll lower their peak demand, but it also lowers their peak demand response capability. So it might get the same effect, but you just have to be careful about double counting. If there's going to be a lot of PV penetration, you can't necessarily assume that DR will grow at the same rate. Just a few other quick barriers that we see. Certainly customer control concerns, so not everyone wants the utility or a vendor to be able to automatically shut down their load, whether it's a homeowner or a building owner. And then there's generally a lack of building automation systems in the commercial building space. So we talk about smart buildings, and there's still a lot of dumb buildings out there. And then third, certainly cost to install a building automation system or to put in a smart thermostat has a cost associated with it. So it's not like there's no economic barrier that has to be overcome, or at least some kind of a return analysis has to be prepared. So go through some examples of state activities, and people might have heard it in New York. They're reforming the Energy Vision Proceeding, or REV as it's known, seen as maybe the most forward-thinking single regulatory proceeding in the U.S. at least in transforming the utility industry. So the way I look at it, Apple just had their big iPhone and iPad announcement yesterday, so I like to think of what the REV wants to do is create a distributed system platform, DSP, which might be like a smartphone, and then they want all kinds of third-party vendors, service providers to put their apps on top of that platform. So that's the analogy I like to make. Now they could have taken a step to say that this DSP should be an independent third party, but at this point the DSP is going to stay the current regulated utility. So it's more of a transition than a revolution. but it's still going to be a change for the utilities and how they manage their system. They have to put together distributed system infrastructure plans, talk about what this will mean if they're going to put in new metering, what other types of systems they'll need, like Sachin was talking about. So a lot of people have their eyes on New York for this REV proceeding. On the other coast, certainly California, doesn't like to be outdone by New York, but there's a little different structure. There's really this three-headed monster in California: the California ISO, the California Public Utilities Commission, and the California Energy Commission that all try to work together, but sometimes are doing things on their own to kind of move the energy construct forward in the state. So from one thing that they've determined is that they've come up with a lot of new terms and acronyms. So the first one is bifurcation, which is a concept that some of the demand response that acts more as a supply side resource, maybe fast response, ancillary services, capacity market, can participate in the wholesale market with the ISO, but things that are more retail, price response, dynamic pricing will remain with the regulated utilities. That's one term. Another one that the California ISO recently unveiled is DERP, D-E-R-P. It's Distributed Energy Resource Provider. So the ISO is looking to allow aggregated resources to participate in its markets, which hasn't really been available before. So that could open up some opportunities starting in 2016. The PUC is doing a lot in terms of valuing DR. So they've had some working groups to determine the values of demand response at different levels of the transmission and distribution system. That, it's kind of a first step to really determine what the value is of DR, to figure out what kind of benefits it can provide. And the PUC is also starting a DRAM, DRAM, demand response auction mechanism, which isn't a full-blown capacity market like you see in other places, but it is a specialized market for utilities to procure demand response. And then the IOUs are moving towards proposing default time of use pricing for all of its customers to take effect in the next few years. So a lot of different activities going on in California. Looking internationally at a high level, you see Europe. We talked about environmental drivers, so there's these 20-20-20 provisions to reduce emissions and be more efficient. So I think that's kind of a unified driver in Europe, although with the way the economy is going, there's a little less pressure, I'd say, on some of those drivers. And then in Asia, a couple pictures here. So it's been a few years now since the Fukushima nuclear accident in Japan, but Japan is still in all the above resources type of mode, so they are working their way towards demand response participation. And then the one below is a picture in China, which you always have to assume that China is going to get into a market at some point. It's just hard to say exactly when and at what scale, but they've done some pilots for demand response as well. So looking at Europe, this is a great slide from the Smart Energy Demand Coalition, who's done a lot of work on demand response in Europe, just looking at the advancements over the past couple of years in market opportunities. So you see that there is more green coming in as time goes on. Places like the UK or Great Britain opening up demand response and capacity markets. France, certainly a big market. The Scandinavian countries have some opportunities. There are still some big red spots there in Spain and Italy. They're staying more of the traditional regulated route. And then just the last one, certainly people talk about Japan and China a lot for Asia, but South Korea might be moving the quickest in this case. So they have a large amount of commercial industrial load, over 80% of their peak load. So the Korea Power Exchange, the wholesale market operator, opened up a DR market in December for about 1,500 megawatts. So it's bid in day ahead, and then it has to reduce when it's called. And just to show the interest here, Enernox, one of the largest DR providers in the world, opened an office to get involved in the market. And energy pool, which is part of Schneider, has partnered with Hyosung, a local South Korean conglomerate, to partner and enroll customers in this market. Now let's finish up with some of our recent forecasts related to demand response spending and sites. So right now, as we say, there's about $200 million of demand response spending, and this encompasses things like controls, communication, metering equipment on the commercial and industrial side, and then on the residential side, it can be things like load control switches and implementation costs for demand response management systems, things that Sachin talked about. And it's almost all in North America, but we see over 10 years it'll get up to about $1.3 billion, and it will expand dramatically in Europe and Asia, as we talked about. And the last thing, just looking at number of DR sites, another way to look at it, so right now is under 10 million DR sites, and now this is skewed towards the residential side because each home is a site, but it'll give a general idea that over in 10 years we'll get up to over 80 million sites, and again, you see a lot of expansion in Asia and in Europe as well as North America. So that's what I had prepared, and I'm happy to hand back to Claire for Q&A.
Brett, thank you very much for that, and thank you very much to all of our presenters today. This was an incredibly interesting webinar, and I have a couple of questions which I'm going to start. I think, let me address this one to you, Sachin, and it's from Chow, who wants to know, is demand response viable in vertically integrated monopoly markets, and if so, why?
So if you look at the United States as kind of a case example, and you look at a vertically integrated utility, there are a lot of vertically integrated utilities that have deployed demand response resources. The primary driver here is that with the appropriate technology and the appropriate level of consumer and the right level of consumer demand-side resources participating, it becomes much more cost-effective to scale up traditional DR than it would be to scale up a traditional peaking plant. So one of the utilities that we work with, their entire business plan was predicated upon, in the next, 10 years, we're going to need to build a peaking plant. If we're able to go through and bring on consumer demand resources, both at the residential level and at the C&I level, we're going to save, enough money to help us go through and upgrade the rest of our technology infrastructure. If you look at a demand response program in and of itself, in most cases, with the appropriate level of technology and the appropriate execution with respect to consumer engagement and the right incentive practices and the right program design, you can scale up a 100-megawatt program fairly quickly, within 6 months, within 12 months, within 18 months, which is a significantly reduced timeline and operating cost when looking at having to build a natural gas power peaking plant or any type of peaking plant. So that's where DR can become viable, because it does present a fairly easy way, or at least an easier way, to have access to another form of what we would say negawatts or generation.
Fantastic. Thank you very much. Char, I hope that answered your question. Remy, now a question for you, which I think that you're quite well positioned to answer, and that is, where do you see active load management in action throughout the world?
I have in mind several examples, especially in Japan. After the Fukushima accident, the Japanese DSO, distribution system operators, they did a lot of work to manage the load, especially during the peak time. And in Japan, the peak time is due to the AC is beginning of the afternoon, when it's quite hot and humid. So they did a lot of things regarding demand response. And I have one example in mind which is quite funny. They are, for example, offering you tickets for a movie. available only for the 8 p.m. movie, because they believe that if you go with your family to see this movie, you will not be at home at the same time, that's obvious, and thus you will not switch on the light, you will not switch on the AC, and you will not cook, and you will do everything once back from the movie, which is nearly 10:30 p.m. So that's quite quite innovative way to manage demand response. So there was this one plenty in Japan. In France, we are doing several as well. Italy and Spain are they have also a very interesting active demand program or demand response program. Iberdrola in Spain, they have a program based on a smart device at home. It's quite a nice small iPad. You have it in your kitchen, for example, and on the iPad you can see real time what you are consuming and the price per kilowatt hour, and thus when it's peak and off peak, you have the complete awareness of what is going on in your home, and it's quite efficient. As you know what is going on, you can change your behavior or be very careful with the light and not to let things on too long if you are not using it. If you are interested more in demand response, and I don't know if you know ISGAN. ISGAN is the smart grid department in the International Energy Agency. ERDF is part of this department, and we, with the support of Accenture, we wrote a demand side management casebook gathering more than 15 different cases from all over the world: Japan, Italy, Spain, France, the US as well, Canada, and you can download it for free, of course. For that, you just have to reach the ISGAN, ESGAN, International Smart Grid Action Network, the ISGAN website, and you can download the book. And I was the coordinator of this casebook, so I will be very delighted if you download it, with several examples of demand response, international demand response initiatives.
Remy, thank you. I think that what we'll probably do is put a link from Metering and Smart Energy International to that book as well. I think that it's probably something a lot of people would be very interested in seeing. A question for you is, why do you think the various regions will or will not grow from a demand response or active load management point of view?
That is for me?
Yeah.
Okay. Sure. Well, I think we gave a lot of the drivers before. So in North America, you see a lot of the renewables coming on board, and you see that in certain countries in Europe as well. So I think that'll be a big part of it, and related to that is just more of the environmental concerns, carbon reductions in those areas. In Asia, I think it's more about just efficiency and being able to keep up with demand growth, and not wanting as many coal plants or fossil fuel plants, or even there's obviously some anti-nuclear sentiment around the world that plays a role. Then you have the other areas. NAVIGANT is actually doing a fair bit of work in the Middle East also, which I didn't talk about, but places like the United Arab Emirates, Dubai, and Abu Dhabi, Saudi Arabia are actually looking to get more. You might not think about them getting into these types of things, but they are trying to be more sustainable and diversify away from just an oil base. So there is activity in those regions. Somewhere like South America, they're a little further behind, but places like Brazil and some other countries are getting more into grid modernization and getting advanced metering. So I think it will come along there at a slower pace.
Okay, thanks. A question here from David, and I think Sash and I would probably direct this to both you and Remy. Perhaps you can go first. And this is from David, who's asking, are there particular security considerations specific to active demand management systems beyond the typical grid security considerations?
So I would look at something like, go ahead.
No, please, go ahead.
Let's say, in this context, I would look at this question with respect to outside of typical grid security, probably in terms of cybersecurity and cybersecurity concerns. I think there's a shift now, and I think part of this is really based on planning when we start talking about being able to provide active load management. And I think there's two components here. There's a cloud-based component and there's an on-premise-based component, and how we actually deal with cybersecurity. And I think a lot of this really comes into play with kind of the long-term planning initiative. With active load management, a lot of this can be driven via integration. And it's being able to integrate to all of the different systems that the utility would have available, whether it's the SCADA system, the EMS system, the automation, the distribution automation system, other forms of consumer load control, whether it's through a load control head-end system, an aggregator, and just other informational technologies behind that utility. And a lot of this depends on, from a long-term planning perspective, if we know that the SCADA systems are going to be integrated into an active load management system and that technology, and that's where you would really have to understand, cloud-based security versus putting it behind a utility's firewall and being able to secure the connections between the SCADA system and some of those other things. So that would probably be my answer. Is a lot of this depends from a cybersecurity perspective. A lot of it just depends on an integration perspective and exactly what systems we're talking about integrating to and what data we're talking about and kind of the control characteristics and the standards and protocols that we would use back and forth.
Remy, do you have any thoughts on that?
Yeah, I fully agree with what Avin just said. Regarding cybersecurity in the GRID4EU, especially in this GRID demo project, what we have based the active demand or the demand response protocol on the smart metering infrastructure, and this infrastructure is quite robust when it comes to cybersecurity. And to contact or to reach the consumers, we are sending text message or email. We, of course, we have in mind to have, for example, an app to allow the consumer to switch things on or off with the phone. But when it comes to an app, we are facing cybersecurity issues. So far, we believe that the smart meter infrastructure is the safest for us, and of course, text message are already safe. But we will see in the coming month or year what we can do. But as mentioned, if we want to involve the SCADA system in the demand response ambitions, we have to be very, very careful, especially on the utility perspective. We cannot open or raise any risks on all SCADA systems. SCADAs are able to manage nearly everything on the utility perspective, so we have to be very, very careful. So far, our recommendation, based on what we have done in the 6 GRID4EU demos, is to use the smart meter infrastructure, which is quite the most robust when it comes to security.
Thank you, Remy. Unfortunately, that is all that we have time for today. If we haven't had an opportunity to answer a question that you submitted, somebody from either OMNETRIC or ERDF or NAVIGANT will be in touch with you to answer your question. Thank you to everybody who participated, to our fantastic presenters, and to OMNETRIC Group for their support and for ensuring that we are able to present such informative and interesting webinars to our audience. The webinar will be available on demand at Metering and Smart Energy International on our website, which is www.metering.com. and you will be able to listen to it and have a look at the slides and everything as of tomorrow morning. If anybody has any questions or if anybody would like to get hold of any of the speakers, please contact us and we'd be happy to pass your details on. On behalf of me, Claire Falkvane, thank you very much for joining us.
Thank you.